get to exceptions to the octet rule. There are 3 types of ions or molecules that will not follow the octet rule. So there are 3 major exceptions. If we have an odd number of electrons, hate that. If we have ions or molecules with less than an octet, so boron is such a good example of that, and beryllium is another good example of that. And then our last one is going to be ions or molecules with more than 8 valence electrons, which is really just called an expanded octet. Let's first look at the odd number of electrons. So this type of exception is really, really, really rare, because most of the time if you have an odd number of electrons, these molecules are going to be unstable, or they're going to be so reactive that we're not going to be able to find them just by themselves out in nature anyway, because nothing wants to have an odd number of electrons. They just don't happen. So an example of that could be I could have an NO, I could have NO2, I could have O2 minus. Another example could be ClO2 without the charge to it. So all of those are examples of odd number of electrons. So ClO2, NO, NO2, and O2 minus. So all of those would give me an odd number of electrons. I would have one that would have this one single electron here. And it's okay if you have that. I've never seen on the AP test where they've given you this, because they are so rare. So I would just, let's know that they exist. We'll appreciate their existence, but we will also appreciate the fact that they are very reactive. So most of the time I don't see them. So we're going to pretend like we don't see them now. Okay. My second type is when I have fewer than 8 electrons. So let's say, for example, we have a boron trifluoride. So I have boron here as my central atom, because fluorine would be the most electronegative. And so that means that fluorines would act as my ligands. And then boron is, I always say that when I'm comparing boron with fluorine. Oh my gosh. Boron is the least electronegative, so it's going to be the central atom. So we know that our rules: find the total number of valence electrons first. Let's attach all of the outer atoms to the central atom once we've chosen that central atom as the least electronegative. And then we're going to fill the octet on the outer atoms first, or the ligands. And then whatever electrons we have left will surround the central atom. If we run out of electrons, that's when we start to form multiple bonds, whether it be a double bond or a triple bond. So in this case, I had enough electrons, so I know fluorines all have a full octet, but boron does not. How do I know if I've drawn the best Lewis structure? Well, remember, we know if we've drawn the best Lewis structure because of formal charge. So if I do any other type of Lewis structure where boron and fluorine have some type of double bond, I'm going to get a -1 charge on boron, and then on fluorine, I'm going to get a +1 charge. Why on earth, for the most electronegative element on the periodic table, which is fluorine, would I ever have fluorine having a +1 formal charge? That makes no sense, versus boron having a -1 charge. If I do my formal charge on the one that we see up here, we're going to see that that's going to be the best, because I get formal charges of 0. So we're happy with this one because it really is truly the best representation. So giving boron a filled octet is going to place that negative charge and a negative charge on boron, a positive charge on fluorine. That's so terrible, because we want negative charge to go with the most electronegative atom. So this is not an accurate picture. These are not an accurate picture of how electrons are going to be distributed in boron trifluoride. So the dominant structure is going to be this. Less important are these. I'm not really ever going to see these. I'm going to see this. So structures that put a double bond are much less important than the one that leaves boron with only 6 valence electrons. So dominant structure versus less important or less dominant, we're always going for the dominant, and you can always find that by using that formal charge, okay? So our lesson: if filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom don't fill the octet of the central atom. So boron will do this, and the other really important one is beryllium. So beryllium and boron are going to be my key players for those. We also have our third type, which is the expanded octet. The third type is the largest class of exceptions, and that's when we have more than 8 electrons in the valence shell. So molecules and ions with more than 8 or more than an octet of electrons around the central atom, we usually call those hypervalent. And other hypervalent species, some could be, I could have SF4, there's ASF6-, there's ICL4-, there's so many of them. And usually we see this happening when we get in, sorry. So sorry. We usually see this whenever we get into atoms that are in the third row or below, and that's because they have so many electrons, they just don't even know what to do with them. So those are hypervalent species, meaning that they fulfill more than an octet of electrons around the central atom. Now, principal reason for the formation is just because of the relatively larger size of the central atom. So the reason this happens is because of the larger size of the central atom. Let's look at an example here. I have PCl5. So the only way PCl5 can exist is if phosphorus has 10 electrons around it. We'll get into the molecular geometry when we get into chapter 9, which is still technically part of this chapter that we're kind of just grouping together. So d orbitals kind of help participate in this. Even though we can draw Lewis structure so this is specifically looking at the phosphate ion. So this says, even though we can draw Lewis structure for the phosphate ion that has only 8 electrons around the central phosphorus, so that would be here, that's here. So I can draw phosphate ion so that I have phosphorus fulfilling an octet and then all of the oxygens around them fulfilling an octet. And oxygen does have a negative 1 formal charge, where phosphorus has a positive 1 formal charge. So the -1 is on the more electronegative element, oxygen, versus phosphorus. So it's not that this is a bad Lewis structure, it's just that there's a better one. So a better Lewis structure would be where I place a double bond between phosphorus and one of the oxygens. So I'm seeing that here. Why is that better? Because now I've created a formal charge of 0 for phosphorus on this one and 0 for oxygen on the other one. If I can have a 0 formal charge, that's indicating that I have more stability in that molecule or in that ion. So I need that to happen. So this is the dominant Lewis structure. The reason that I posted phosphate on here is because that is the most commonly missed Lewis structure on the AP test. They love to give phosphate, and they love to give phosphate because like 80% of students will draw this one. And it's not bad, it's not wrong. It's just that this one is better. And it's solely based on the argument that formal charge here is better for 2 of the atoms than formal charges on 2 of the atoms over on that one. So lesson for the more than 8 electrons. When the central atom is on the third row or below, and expanding its octet eliminates some formal charges, then that's what we want to do. So I expanded phosphorus's octet here by placing really 10 electrons in its octet, but I've created much more stability because this has a formal charge of 0 and that one oxygen has a formal charge of 0. So you don't have to worry about this, guys, because you're about to do exceptions to the Lewis structures now. So if you would please, Ava or Trevor or Annie, if you would pass out the Lewis structure paper that was the first Lewis structure paper that's on top, give a copy of that to everyone, and then we are going to, somebody then can pass out bags of pretzels and M&Ms. Annie is going to partner you up, and then kind of break your desks up into groups as well. When you're done modeling all of them, please eat your M&Ms or Red Hots or pretzels. And there may be a couple of extra bags up there. If you want one extra bag, please take that and eat those as well. After this, I think Annie knows the rest of the drill, or Ava or Trevor know the rest of the drill. You'll break up into groups, bigger groups. 5 big groups is what you're going to make, and do another set of Lewis structures. And then after that, you'll do your pre-lab in your lab notebooks, as well as your lab procedure. We'll do lab tomorrow. And then also, you'll have a video. It'll be posted already. So if you want to watch it now, or if you want to watch it after you do your Lewis structures, please feel free to do that. And then, if not, that will be your homework, okay? I will see you tomorrow. I can't wait to see your smiley faces. I've missed you guys so much. I hope that your day that I didn't see on Tuesday was good. And then I also hope you had a good PSAT testing yesterday, even though I can't imagine that you did because it was a test. I will see you tomorrow. Have a great day. Bye, guys.